Hi, I'm Bob. Welcome back to the 5 Minute Econometrics, an econometric tutorial for basic concepts and estimation methods. Today, we will explore the 6 classical assumptions for linear regression models. They are from the textbook Introductory Econometrics, a Modern Approach, the 7th edition by Professor Wooldridge, and the textbook Econometric Analysis, the 8th edition by Professor William Greene. The first assumption is linear in parameters. The population model can be written as follows, where betas are the parameters and the epsilon is an unobserved random error or disturbance term. We can write it in matrix form. The lowercase letters in bold are vectors, and the uppercase letters in bold are matrices. This assumption implies that the betas cannot take the logarithmic or squared form. They should be in the level form. However, the variables in the model can take the logarithmic or squared form. In other words, some unlinear relationships between variables are allowed in the model. For example, all of these models satisfy the linear in parameters assumption. The assumption is for the population model. In William Greene's textbook, it is also called the underlying data generating process. It describes the real relationship between variables, and the population parameters represent the ceteris paribus or causal effects of the explanatory variables on the outcome variable. The second assumption is the random sampling assumption. It is about the sample we use. We assume that the sample is a random draw from the population. So, the sample is representative of the population, and we can use the sample to estimate the population parameters. The third assumption is the no perfect collinearity assumption. It is also about the sample. There is no exact linear relationship among the explanatory variables. In the simple regression, there is only one explanatory variable. The no perfect collinearity assumption is equivalent to the sample variation assumption. When the only explanatory variable does not take the same value for all its observations, it will not be perfectly collinear with the constant term. The no perfect collinearity assumption in William Greene's textbook is also called the full rank assumption. The reason is that if there's no exact linear relationship among any of the explanatory variables, the matrix of the explanatory variables X has full rank K. A full rank matrix of the explanatory variable is the necessary condition for us to compute the OLS estimates beta hat. The fourth assumption is the most crucial assumption. It is called the zero conditional mean assumption in Wooldridge's textbook and the exogeneity of the explanatory variables assumption in William Greene's textbook. The error term epsilon has an expected value of 0 given any values of the explanatory variables. It concerns the relationship between the explanatory variables X and the error term epsilon. All the unobserved factors are in the error term. This assumption implies that the unobserved factors or the omitted variables are not correlated with the explanatory variables in the model. When it holds, the explanatory variables are the exogenous explanatory variables. This is the key assumption to show the OLS estimators are unbiased or consistent estimators of the population parameters. Using the above 4 assumptions, we can prove that the OLS estimators are the unbiased estimators of the population parameters. The explanatory variables x are not correlated with the error term or disturbance epsilon, which implies that no observations on x convey information about the expected value of the disturbance. With the zero conditional mean assumption, we can write the expected value of y conditional on x as x times beta. X times beta is called the conditional mean function, and it is the regression model we estimate. That's why we usually say on average or expected to change in our interpretation of the estimate beta hat. The 5th assumption is the homoscedasticity assumption. The error term epsilon has the same variance given any values of the explanatory variables. The above 5 assumptions are collectively known as the Gauss-Markov assumptions, and we can prove that the OLS estimators are the best linear unbiased estimator, blue, under these 5 assumptions. The homoscedasticity assumption is not needed to prove the unbiasedness of the OLS estimators, but it is needed to compute the variance of the OLS estimators. The 6th assumption is the normality assumption. The error term epsilon is independent of the explanatory variables and is normally distributed with zero mean and variance sigma squared. This assumption is for us to obtain the exact sampling distribution of T statistic and F statistics, so that we can carry out hypothesis tests. That is, it is for the statistical inference after the regression and a starting point to construct the test statistics. However, if we have a large sample, we can drop the normality assumption because the OLS estimators are asymptotically normally distributed in large sample size. Thank you so much for watching this video. See you soon on the next topic. Goodbye. Thank you for watching this video and subscribing to my YouTube channel. See you next time.